Okay, thank you so much. So yeah, I'm going to talk about the Lefschetz property for Artinian complete intersection, and I want to start defining what is the weak and the strong Lefschetz property. So during this talk, R for me is the standard graded polynomial ring over a field K that for most of the results, we also require the K is algebraically closed field. A is a Artinian, graded Artinian algebra of so-called degree S. So S is the maximum degree of any element in A. We say that A has the weak Lefschetz property if exists a linear form such that the multiplication map between degree I and degree I plus 1 has maximum rank for each degree. So it was always or injective or surjective. In that case, L is called Lefschetz element. This Lefschetz element form a Zariski open set. And so when we have the Lefschetz property, it's also interested in studying the non-Lefschetz locus. That is, as a set, is just all the elements that fail to be Lefschetz element. And this is studied by Emanuela, Mirai, and Nagel first, and they studied the non-Lefschetz locus as a subscheme of the dual projective space. Okay, so the other definition that I want to give is the definition of strong Lefschetz property. We say that A has a strong Lefschetz property when exists a linear form such that the multiplication map for any power of L, so L to the D between forms of degree I and degree I plus D, has maximum rank for any possible I and for any D that in this case we call range D. Okay, so these are the definitions. And let's start with an easy example. Let's take the polynomial ring with two variables and assuming characteristic 2. This has the weak Lefschetz property, but it does not have the strong Lefschetz property. To prove that it has the weak Lefschetz property, we can consider just the multiplication map times x1. Clearly, until a to the 3, this map will be injective because I mod out only for something of degree 4. Let's check the map between A3 and A4. I can just write down the basis of as a vector space between A3 and A4, and I can notice that multiplying from here to here by x1 is surjective. Since we are in a standard graded case, this map surjectives means also that everything after that will keep being surjective. And this proves that my x1 is a Lefschetz element, and so I have the weak Lefschetz property. I don't have the strong Lefschetz property because if I take any linear form, okay, I can write it like ax1 plus bx2, and I consider the multiplication for L to the third, but this map takes the element L that is in A1 to 0 because we are in characteristic 2, and we are mod out by x1 to the fourth and x2 to the fourth. And this is true for any linear form that I choose. Therefore, this map cannot be injective. For dimension consideration, it cannot be surjective neither, and hence it does not have maximum rank. And so that's why we don't have the strong Lefschetz property. Okay, as I said in the title, I'm interested in complete intersections. So when the ideal I is generated by a regular sequence, but since we are also in the hypothesis that I need to be Artinian, then it's the same thing. Since I'm Artinian, then I want I to be Artinian and generate by exactly n elements to be a complete intersection. In the example before, it was a complete intersection. So a very important theorem that actually is one of the theorems that started the study of the Lefschetz property is the theorem of Stanley that said that any monomial complete intersection over a field of characteristic 0 have the strong Lefschetz property and therefore also the weak Lefschetz property. As we already see in the previous example, characteristic 0 here is very important because the example before was a monomial complete intersection in characteristic 2 that fails the strong Lefschetz property. And in fact, the first part of this talk, mostly of this talk, is focused in characteristic P. And then we can ask when a monomial complete intersection have the strong Lefschetz property, and when a monomial complete intersection have the weak Lefschetz property. The end of the talk inside is like aimed to talk about characteristic 0. And in characteristic 0, we have different type of question because we know the monomial complete intersection have the weak Lefschetz property and the strong Lefschetz property. And we can ask, okay, is it true also for any complete intersection? And in the case when we have the weak Lefschetz property, can we study the non-Lefschetz locus, so the forms that fail to have maximum rank somewhere? Okay, so the first part of the talk, as I said, we are focusing characteristic P and monomial complete intersections. Let A be my monomial complete intersection. So I mod out by x1 to the a1, xn to the an, and I assume a1 to an increasing. Clearly, if I have just one variable, I have the strong Lefschetz property. Also, if the so-called degree, that in this case is just the sum of the degrees minus n, is smaller than p, then I behave exactly as in characteristic 0, and therefore I have the strong Lefschetz property. Okay. To classify which other monomial complete intersection have the strong Lefschetz property, we divide the case p equal 2 and p bigger than 2. For p equal 2, this characterization is due to Cook that prove the first of all, the strong Lefschetz property is possible only in 2 variables. And even in 2 variables is possible if and only if the first of the degrees is 2 and the other one is odd, or if the first of the degree is 3 and the other one is congruent to 2 modulo 4. So we have very few cases where we have the strong Lefschetz property. For p bigger than 2, we also have a classification due to Ludwig and Nicholson. They classify all the monomial complete intersection have the strong Lefschetz property. And I want to point out that even in this case, clearly is possible also for bigger variables, but the case n equal 2 behaves very different than the others where we have more algebras that can have the strong Lefschetz property. Okay, so how we can see in this slide, the classification of the strong Lefschetz property is basically done. We have a full picture of what's happening. And so the natural question is, do we have something similar? Can we ask which are the monomial complete intersection having the weak Lefschetz property? And this is the question that I'm interested in, and what I'm saying right now is all a joint work with Claudio Raicu, Ethan Reed, and Annette Kumakongi. And we want to focus as first in the case p equal 2. I need an extra definition. Let's take any integer, and q is a power of 2. R is the remainder of the division modulo 2 times q. Okay? Then we can define this function here, theta q of x, that goes just to r if this remainder is smaller than q minus 1. Goes to 2 times q minus 2 minus r if the remainder is between q minus 1 and 2q minus 2. And finally, the last possible case is when the remainder is exactly 2 times minus 1 is minus infinity. It is the remainder of the division but divided by 2q, not q. That's why we have these 3 cases. Using this formula, the result, together with Kumakongi, Raicu, and Reed, is that we classify which monomial complete intersection have the weak Lefschetz property, and a monomial complete intersection have the weak Lefschetz property if and only if this formula here holds for any power of q that is between this dim sum and 2 times an minus 1, where an is the biggest of the degrees. Instead of explaining this formula, I want to explain doing some examples. Let's consider first. The Artinian algebra monomial complete intersection where I mod out by x1 to the 9, x2 to the 11, x3 to the 13. I didn't tell you what is the 9 sum, but trust me on this, if I do in sum of 8, 10, and 12 is 14. Okay, so let's black box this, but okay, if I take the p-adic expansion and some component on component on, that's why I didn't want to go into that. So the theorem said that what we want to do is checking that's inequality for any power of 2 between 7 in this case and 24. Okay, then we have to check only for Q equal 8 and Q equal 16. Those are the only one that we need to check. For Q equal 8, all 8, 10, and 12 are in the second case of my theta function. So theta of 8 is 6, theta of 10 is 4, and theta of 12 is 3. Then we can check that when I go to sum all of these, the sum is 13, that is less or equal to 2 times 8 minus 2. So this is fine. The other case that I need to check is 16. 16, since 8, 10, and 12 are strictly less than 16 minus 1, the theta function just take them to themselves. So when I go to sum all of them are 30. That is again less or equal to 2 times Q minus 2. And then we are done. These are the only two cases that I need to check, and therefore A has the weak Lefschetz property. I want to do a similar example, but very different actually. I got to just change 1 degree. Between 13, it becomes 14, okay? I'm taking the nim sum, in this case as 15. Then I have to check the equality again, and the only case that I have to check is for Q equal 8 and 16, as before. This doesn't change. Let's go to check what happened for 16. I take the theta, also in this case, it's just itself, but when I go to sum them, the sum is 31. That is strictly bigger than 30, and therefore I know that the face the weak Lefschetz property. I don't need to check anything else. Any question on this? Yes?
Are you able to find the weak Lefschetz element when you calculate?
I mean, since we are in monomial complete intersections, the sum, if I have the weak Lefschetz, the sum of the variable will be a weak Lefschetz element. So yes, yeah. Okay, and this concludes the case for characteristic equal to. What's happened for characteristic bigger than 2? First of all, we know that the weak Lefschetz property always holds for n less or equal than 2, so for n equal 1 and 2, and also hold when the Sokal degree is less or equal than 2p minus 2. Unfortunately, up to now, we do not have a complete characterization of which one have the weak Lefschetz property, but I can tell you which one are the Sokal degree that automatically will give me the weak Lefschetz without independent by the choice of A1, AN. This, again, is a result with Kumahonji, Raiku, and Reed, and we prove that all complete intersection of Sokal degree S satisfies the weak Lefschetz property if and only if we have or one of the conditions above is true, or n equal 3, and this inequality holds. And after that, we have only one more case. When n equal to 4, p is 2, and s is 6. This is the only cases. So what I mean with this is that if I take any other Sokal degree that is not between these, then I will have at least one complete intersection of that Sokal degree that fails the weak Lefschetz property. Okay, I would like to just mention a bit how we got these results. So what we noticed is that proving that a monomial complete intersection as the weak Lefschetz property is equivalent to go to check if a monomial, that monomial there, appears in the character of this shift cohomology group, where d to the dd is the divided power function, and r is the shift of the cotangent shift of Pn minus 1. And also we have the d plus c is equal to the Sokal degree. So we notice this, and then from the result of Gao and Raiku that characterize exactly when these groups are 0, we were able to see which Sokal degree imply the weak Lefschetz property, because in those cases, the groups were 0. And for a characteristic equal to 2, in Jane Warwick, Makonji, Raiku, and Reed, we have a closed formula for these characters. And from that, we were able to have the classification. I want just to say that for P strictly bigger than 2, we do still have a formula for these characters, but these are a recursive formula. And that's why we don't have yet a classification for P bigger than 2. Okay, but I think that like the thing that I want to say about this proof is basically that you prove weak Lefschetz property as an application of study these cohomology that are actually equivalent to study the cohomology of line bundle over the incidence correspondence. Okay, this concludes the part of characteristic P of my talk. And now I want to shift to characteristic 0 and specifically talking about the non-Lefschetz locus. Let's recall what we know. We know that in characteristic 0, every monomial complete intersection has the weak Lefschetz property and the strong Lefschetz property. This also means that a general Artinian complete intersection of degree d1 dn will have the strong Lefschetz property, so like with general coefficients. Is a conjecture that every complete intersection has the strong Lefschetz property. This conjecture is actually very widely open. The only case where is proved completely is the case of 2 variables, where we have the strong Lefschetz property. Actually, Arima, Migliore, Nagel, Watanabe proved that any Artinian algebra in characteristic 0 in 2 variables have the strong Lefschetz property. The case, though, that I want to focus for the last 3 minutes is the case in 3 variables. Here, Arima, Migliore, Nagel, and Watanabe proved that the complete intersection have the weak Lefschetz property, while up to now, the strong Lefschetz property is open. But Boy, Migliore, Miroy, and Nagel also study the non-Lefschetz locus of this Artinian complete intersection and prove that for a general complete intersection, the non-Lefschetz locus is a finite set of points if the so-called degree is even and D3 is smaller than the sum of the other degrees, and is a hypersurface otherwise. So the question I want to answer is, okay, can we extend this and maybe instead of linear forms, we are going to look forms of degree 2. So does exist a form of degree 2 that has maximum rank? And if so, can we study the ones that fail to have maximum rank? So the first result that I want to say is that any complete intersection, characteristic 0, in 3 variables has the strong Lefschetz property arranged 2. What I mean with this is there exists a linear form such the multiplication map times L square from degree I to degree I plus 2 has maximum rank for all i's. And then the next question is, okay, then now that we know this, can I study the forms of degree 2, not just squares, but any form of degree 2, that fails to have maximum rank at a certain point? We can define, exactly as we define the non-Lefschetz locus of form of degree 2. Just taken as a set is just the forms that fail to be injective and surjective somewhere. Then, in the case of monomial complete intersection in 3 variables, like this, we know that this is a positive cos dimension because we know there exists at least a conic that behaves well. And moreover, it turns out that in this case, we have a determinantal structure if I consider this as a subscheme of P5. What I was able to prove is that for a general complete intersection, the expected codimension, since I have a determinantal structure, is achieved. Specifically, the codimension is 1 when the so-called degree is even, or D3 is bigger than the sum of the other variables. If codimension 2, when D3 is equal to D1 plus D2, and is 3 if the so-called is odd and D3 is smaller. Okay, so one thing that I just want to point out before concluding is that here this theorem holds only for general complete intersection. Okay, in fact, if I go to look at monomial complete intersection that are not general, and for example, let's do the case where the expected codimension should be 3, but I can show you examples where I have codimension 3, 2, or even 1. And since I already knew that there was positive codimension, means that like I have example for all the possible codimensions. Okay, thank you so much.